NH2 right under C, and I'm going to actually draw it out. Okay, so, and actually I'll draw this one out too because. Alright, so this is a balanced molecule, right? But there are no charges on the molecule. CH3 has no charge, it's totally non-polar. So we'll put that that's our. So this is the same molecule, okay? But at a pH that or not. Okay, I'll give it a second. And then putting the third H on here is a little bit tricky because you know you've got the like the. See if I can do it. Right. So that's my going out. So this is still alanine. Okay. So this is our Zwitter ion, right? There's still no net charge to this molecule, but what's happened is that due to the pH in the environment, the H has hopped off of our carboxylic acid and hopped on to our N. This doesn't change the net charge in the molecule, but it does change the way the molecule behaves. The reason that I'm drawing this and pointing it out is because a lot of chapter 5 that we're going to gloss over because we're assuming you got done with chemistry is based on this idea. We're talking about primary, secondary, tertiary, and quaternary structure. Those things happen because that happens, and because there are charges on the R groups. And at different pHs, those H's hop on and hop off. The other thing that the R group has is hydrophobicity or hydrophilicity, which we looked at that chart and there were two different columns. There's the pKa and the P, well, there's the COH as well, but okay, and the hydropathy index. Okay, so this is the R group pKa. These two are whether or not they're going to go Zwitter ionic instead of just staying in their non-charged on any way configuration. And this tells you whether or not the R group is polar or non-polar. Those things are related, but they're not exactly the same. Okay, so polarity is a measure of whether or not you're going to mix with water, right? Charged molecules tend to mix with water because they have charges, and water is interested in charges, right? So water, you guys remember what water looks like? Right? But it's not straight. Water has this bend in its bond, and what that does is it gives it all kinds of relative mini charges, right? You guys remember these little? Are we going too far afield?
No. Partial
okay.
positive, partial.
Yeah. So partial positive and partial negative charges, okay. And then some molecules. Then we're talking about dipole moments, and how are we doing? Dipole moments? Okay. All right. We're all good. Okay. I never know, you know, because it's people take chemistry 20 different places. So, okay. So water, because it has partial charges, right? It has this ability to interact with molecules that either also can have partial charges or that have total charges. So in general, that confers a high degree of hydrophilicity, water loving. Hydrophobic molecules are molecules that are carbon and hydrogen chains, right, or hydrocarbon chains. They don't really do any of this. They don't move the charges around in such a way that you end up with dipole moments or partial positive or partial negative charges, which means that they're very hydrophobic. There's no way for them to interact with the water and slot in here if this is like a partial negative, or hang out over here if it's partial positive. They don't form that interaction, so they tend to repel. The simplest version of this is oil and water, right? Oil is just hydrocarbon chains, tons of hydrocarbon chains. Water is all of these molecules. They just don't want to mix, so the ones with charges interact with each other, right? And the ones with hydrocarbons interact with each other. Like attracts like. When you need an organic solvent, or when you need to break up something that's organic molecules, you need an organic solvent. Okay, when you need to break up something that's inorganic, you go with an inorganic solvent. And that I know we're now going into is a
different direction. But the idea is like attracts like.